Have you ever found yourself in the situation where your phone overheated and you had to wait for it to cool down again before you could use it? Now, have you ever set your coffee down, walked away, and come back to find it ice cold, so you had to throw it in the microwave to reheat? So these are both examples of heat transfer, which plays an important role in many parts of everyday life, from cooking your dinner to reheating your coffee, cooling your electronics, or keeping your car from overheating. Now, in our case, we're looking at heat transfer in a water heating system. We're developing a water heater in an enclosed vessel. Now, for this system, an optimized heatsink is vital for heating water. But the design is complicated by many different interacting factors. So we set out to determine which of these factors would boil water the fastest. To find out, we designed a 5-dimensional factorial experiment using jump statistical discovery. We created 3D models of 32 possible designs using Fusion 360 and simulated time to boil in a covered container using COMSOL Multiphysics simulation software. We deviated from traditional research methods by integrating factorial design and finite element analysis to explore interactions missed by one factor at a time methods while saving time and resources. Now, I'll discuss this more a little later, but briefly, we were able to collect 16 data points for each level of each factor in a total of 32 runs instead of the 96 runs it would take in a one factor at a time approach. In this experiment, we looked at 5 different factors with 2 levels each. We looked at fin material, where we compared aluminum to copper. We compared a linear and a circular fin configuration, a rectangular versus an inverted trapezoidal fin geometry, and we looked at a sparse spacing of 5 or 6 fins, depending on the configuration, versus a dense spacing of 9 fins, and we looked at 2 different thicknesses. We looked at a 1.06 millimeter fin versus a 1.6 millimeter fin. So once we created the models, we ran the simulations and collected data every 10 seconds. On the left, you can see a heat map that shows the temperature distribution throughout the system at a given point in time. On the right, you can see a histogram that shows a range of boiling times. You'll notice that 4 different models share the fastest time, and 3 models show the slowest time. Between the fastest and the slowest, there is a difference of 4 minutes. Now let's look at these plots. On the left, you can see the effects estimate in blue, which show the result of varying one factor in either direction from baseline. So for example, using a linear configuration would subtract 60 seconds, while using a circular configuration would add 60 seconds, for a total difference of 120 seconds between configurations. Next to it in green, we have p-values, which in simple terms shows the probability that we would be wrong if we said 2 things we're comparing are different. So we want to have a low p-value, and we used a cutoff of 0.05, meaning if we said 2 values were different, there's only a 5% chance we would be wrong. So as you can see, there were 2 factors that did not survive that cutoff on their own, but they did in combination with other factors. Now, if we look on the right, this shows the main effects of each factor on boiling times. You can see once again the dramatic effect of the configuration. So looking at the 2 factors that didn't survive the cutoff for p-value, it would appear that the rectangular fins performed slightly better than the trapezoidal fins, and copper performed slightly better than aluminum, but we can't actually make a claim of significance for either of those. Now here's where things get really interesting. This figure shows the effects of different interactions on boil time. First, I want to draw your attention to the data in pink shown on the right-hand side. Notice first the difference in slope of the line. This indicates that there's a greater difference due to thickness in aluminum than in copper. Now remember, on the previous page, we saw slightly better performance in copper when looking only at the main effects. But now looking at these interactions, we see that aluminum had both the slowest and the fastest boil times. Next, let's look at the data shown in green in the center of the graphic. This shows the interactions between configuration and geometry. In a circular configuration, the trapezoidal fins performed better than the rectangular fins, but in a linear configuration, the rectangular fins performed better than the trapezoidal fins. So we're able to see these complex interactions only because we used a factorial analysis approach. And these would have been missed if we'd used a simple single factor at a time approach. So what does all of this tell us? Which design is the best? So recall from the histogram that there were 4 models with the fastest time and 3 models with the slowest. But analysis of the data shows that there's only one best and one worst. So the worst was an aluminum heatsink with thin, sparsely spaced rectangular fins in a circular configuration. The best was an aluminum heatsink with thick, densely spaced trapezoidal fins in a linear configuration. Now for practicality, we selected an aluminum heatsink with thick, densely spaced rectangular fins in a linear configuration for fabrication. I would like to acknowledge several people and organizations for making this research possible. First, Dr. Benjamin Aleman for his mentorship, guidance, support, and confidence in me. Next, I would like to acknowledge the McNair Scholars Program and the National Science Foundation for providing necessary funding for this endeavor. And finally, I'd like to thank Dr. Christabel Dragoo and the entire McNair Scholars community for the encouragement and support. Thank you.